Hi, I'm Coach Cowland, and in this presentation we're going to look at Newton's law of universal gravitation. So before we begin, let's ask a couple of questions about gravity. What is gravity? What has a gravitational pull? And where would you see the effects of gravity? Mull these questions over, jot down some answers while you pause the video and hit play when you're ready. Okay, so gravity is one of the four fundamental forces of the universe. Gravity is always a pulling force. It is always a force of attraction. Now you'd see gravity in many places, as you probably already know. Gravity is the force that keeps the planets orbiting around the sun. It's the force that holds the galaxy together. It keeps our feet firmly planted on the ground and stops us from floating away or doing perfect slam dunks whenever we want to. And whenever we throw a ball up, it's the thing that brings the ball back down to earth. So here's an example of the force of gravity in action. So you can see here that this is a double-ended arrow because the force of gravity acts on both objects. The force of gravity on the Earth pulls the Earth towards the Sun and keeps it rotating around it. That same force with the same magnitude pulls on the Sun. Now, the Sun doesn't rotate around the Earth, and that's because of Newton's second law. Newton's second law says that the force divided by the mass is equal to the acceleration. And because the mass of the Sun is far greater than the mass of the Earth, the movement because of the Earth is far smaller. So here's some things that you might not know about gravity. Gravity is a field force. This means it acts without contact. There is nothing that is necessary to exist between two objects for there to be a gravitational force between them. This means that things in the vacuum of space have gravitational forces that work perfectly between them. Gravity does indeed go on beyond the confines of the Earth. Anything with a mass applies a gravitational force on any other mass. This applies from the largest things to the smallest things, from clusters of galaxies to subatomic particles. Anything that has any kind of a mass will attract any other thing that has a mass. Here's one that sometimes is a little surprising. Whenever the Earth applies a force on you, you apply an equal and opposite force on it. Why is this? Well, this is Newton's third law. Every action has an equal and opposite reaction. So you might not think it, but when you drop a ball bearing on the ground and it falls and you say, well, gravity is acting on the ball bearing. Yes, it is. But gravity is also acting on the Earth, trying to pull the Earth up to that ball bearing. A common misconception that many people have is that when you're in space, you experience no gravitational pull of the Earth. That's actually not true. Um, Astronauts, when they are in space, the effects of gravity that they feel are negated by the fact that they are traveling so fast around the planet. Um, they actually experience what's called microgravity. But we can do calculations and find out what the gravitational pull is at the altitude of things like the International Space Station and find that the actual effects of gravity, if they were completely stationary, would be very high, which is why when satellites slow down enough, they fall back to Earth. It's only because they are traveling so fast that they manage to stay in their orbit and experience the effects of virtually no gravity. However, they are experiencing the gravitational pull of the Earth as well as experiencing the gravitational pull of many other objects. So gravity is an inversely proportional law. It's very strong when things are very close together and gets weak extremely quickly, but it has a very long reach. This means that the gravitational pull of the Earth, the Sun, the Moon, and various other planets are measurable here on Earth. In fact, the tides are caused by the gravitational pull of the Moon. The equation for Newton's law of universal gravitation is Fg, the force of gravity, is equal to capital G, which is the universal constant of gravitation, and we'll give you the value for that in a minute, times the masses that you're measuring the force between, divided by the square of the distance between their centers of gravity. Now it's very important that this is the distance between their centers of gravity. When measuring the force between the Earth and the Sun, you would measure not from the surface of the Earth to the surface of the Sun, but actually to their hearts, the centers of both of them. So the universal constant of gravitation is an extremely small number, 6.673 times 10 to the negative 11, with units of Newton meter squared per kilogram squared. So let's try a practice problem. Luke Skyhopper has a mass of 85 kilograms. His center of gravity is 3 meters from a 1.2 kilogram laser sword. What is the value for f of g between him and his laser sword? Now I've highlighted here all of the key pieces of information. When I list them down, here they are. I'm looking for the gravitational force of attraction between him and his laser sword, and I've got all my other variables here. When I draw a diagram, I can see the distance between his center of gravity and the center of gravity of the laser sword, his mass, and I've labeled all of these things there. Putting them into a calculation, I can see that the gravitational force of attraction is 7.6 times 10 to the negative 10. So that means that it's very unlikely that he's going to be able to attract his laser sword using the force of gravitation. Escape velocity is a little different. This is the initial velocity that an object needs in order to break free of the planet's gravitational pull. Before we go on to this, let's just discern here one thing. The escape velocity is not the velocity that something, say a shuttle or a rocket, needs to get into orbit. It's the escape velocity of something. Say you were to fire an arrow, the escape velocity would be the velocity that the arrow needs to have when it leaves the bow in order to break out and away from the planet and not turn around and come back down again. Okay, thanks for watching.